Good evening, folks. We have an equation which involves the ceiling function and the floor function. So the ceiling function is kind of the overarching function. So let's remember what that means. Let's use a numerical example to motivate the process we'll use to solve this problem. Let's say we have the ceiling of 29.4, okay? Now the floor of this would be 29, but the ceiling is 30. Okay, and that's simply because 29.4 is bounded above by 30 and below by 29. Okay, notice we do have less than or equal to. The ceiling of 30 would be 30. Just it's a similar this to the floor thing. But anyway, this statement right here more or less encapsulates this definition. It's a special case of the definition of what the ceiling function is. Notice it's not a rounding function. Okay, it's not a rounding function. It is the ceiling function. And this is the reason why. Now, we're trying to find the solution set of the ceiling of a linear expression that contains the floor function. So it's not a trivial problem. We use, the reason why I showed you this is because that would motivate this right here. You see with the 29 and the 30, it's the same as right here, except we're dealing with variables, not a concrete real number, okay? Now, this gives us a set of inequalities. What did I do here? I just did some algebra right here, it looks like. Yeah, folks, what I did some algebraic manipulation to get this to happen, right? I got the x isolated because we are seeking the solution set, right? But we still have the floor function to deal with, and the best way to do it that I know is just to appeal to the definition of the floor function. And we get this statement, which is similar to the ceiling statement, except it's the inequalities are a little backwards compared to that. Now, so now we're trying, so what I do is I just use the k that's guaranteed to exist based on the definition of the floor function. And so we got everything in terms of k, where k is just equal to the floor of x. Okay, k is equal to the floor of x. Okay, now we carry on here using this truth, using this definition of what the floor function means. We get another set of compounding inequalities where it's the k. Okay, we're trying to find out, we're actually trying to figure out a value of k that'll make this work. Okay, and then we'll just substitute it back in up here to get our solution. Okay, you see, if we can find a k that will work, we'll be in good shape because our floor is equal to k. All right, now, and remember, k has to be an integer. Now, the manipulations result in this. When you manipulate this left-hand side, you get this statement. You guys can verify it. I've double-checked. When you manipulate the right-hand side, you get this statement right here. And so this would lead to what? If you divide 9 over 14, you'd have 9 over 14 strictly less than k, or its k is greater than 9 over 14. Remember, k is an integer though. Now, but over here we end up with, what do we have? K is less than a number that's bigger than 1, right? That would be 28, is that 15 over 14? So we get k is less than or equal to 15 over 14. Or, yes, 15 over 14, but notice that 15 over 14 is bigger than 1, right? And remember, our definition of the floor function intimates that k has to be an integer. Well, there's only one integer that is between 9 over 14 and 15 over 14, and that would be k equals 1. Okay? So you see we're close to the finish line here because we can take this k equals 1. We can take the k equals 1, come back up here, and substitute it into this statement, folks. We're going to, in other words, remember, k is the floor of x. K is the floor of x. All right, and so what we'll get here, let's see if I have the room. we'll have 29. There's one right here, so this will be what? 12 over 11 right here, folks. 12 over 11. And y'all, again, one more time, the k is the same as the floor of x, and we found k to be equal to 1. Okay, and then, so we got 12 over 11 is less than x. And then right here, this, again, k is equal to the floor of x, k is equal to 1. So we get 30 minus 17 over 11, which is 13 over 11. And this will be a less than, this will be a closed interval right here. This will be less than or equal to. Less than or equal to, like that. Okay, so that would be our solution set, folks. That is the solution set of this equation. A lot of people would write this as, let's say, 12 over 11 open, like this, in the half open, half closed, however you want to characterize this. And then we have 13 over 11 closed. And you can verify quickly, right, that 13 over 11 is a solution here, right? If you do 13 over 11, you get 13. Well, you'd have to do some work, right? A little bit of work, a little bit of calculation. But 13 over 11, it would make it true exactly. I think it would end up being 30 exactly. All right. Now, another one you can try if you want, just for experimentation. Again, I'm not going to do the calculation for you. But 12 over 11 is not part of the solution, but it does determine the boundary. But 12 over 11 is equal to what? 48 over 44. And so what you could do is just add 1/44 to this. This would give you a solution of x equals to, this is just a candidate or an example, 49 over 44, right? See, I just bumped it up by 1/44, right? Is that right? Yeah, 49 over 44. So you see, that's still going to be a value. That's still going to be a value in this set, right? This x will be a member of this set. And you could check this just to see if I know what I'm talking about. This concrete example, 48, 12 over 11 or 48 over 44 is not in this solution set, but we just bumped it up by 1/44, which certainly is going to place it in this set, right? So this would be a concrete example. But there, in fact, there's an infinite number of real numbers in this solution set. This is just a concrete, rational solution. But again, this is the answer to the question. I consider this a marginally challenging question because it involves the nesting of a floor function inside of a ceiling function. And it's easy to get stuck on something like this unless you stop and realize that you have to appeal directly to the definition of the floor function and get a bound on the k, so to speak. And then that, once you get that bound going, it's just some work, some manipulations with inequalities, I think. But anyway, I'm pretty sure this is correct. Let me know if you spot a mistake. I double checked it, and I'm pretty sure I got it right. So anyway, that is all. Thanks for viewing.